Welcome back to the Learning Studio. You're watching our mathematics series, and today we begin an exciting new section: data, algorithms, and computation, the mathematics that powers modern computer science, optimization, and artificial intelligence. If you're new here, don't forget to follow us by clicking the link below. And remember, the full playlist is waiting for you in the description so you can enjoy the journey from the very beginning. Our topic today is combinatorics, the art of counting, arranging, and structuring possibilities. It may sound simple, but without it, we wouldn't have search algorithms, efficient data analysis, or even an understanding of algorithmic complexity. Imagine you're designing a password system. If you allow just lowercase letters, you already have 26 options per character. Add uppercase, numbers, and symbols, and suddenly the possible combinations skyrocket into billions or even trillions. This explosion of possibilities is where combinatorics comes in. It's the mathematics that helps us count, analyze, and navigate these vast spaces of choices. Core concepts explained simply. Here are the essentials. Counting principles. The foundation of combinatorics, permutations, combinations, and the pigeonhole principle help us understand how many ways things can be arranged. Graphs and paths. Combinatorics studies networks and connections, essential for designing search algorithms like shortest path or traveling salesman solutions. Complexity analysis. By analyzing how possibilities grow with input size, combinatorics helps us understand why some problems are easy while others are computationally hard. Applications in search. From Google search engines to database queries, combinatorics is behind the algorithms that filter through enormous possibilities to find the best answer quickly. Why it matters in AI, computing, and technology. Combinatorics is everywhere in modern science and technology. In complexity analysis, it shows us the difference between polynomial time solvable problems and those that may take exponential time. In search algorithms, combinatorial optimization helps AI systems navigate huge solution spaces efficiently. In machine learning, combinatorics is applied to feature selection, neural architecture design, and hyperparameter optimization. In cryptography, combinatorial explosion is what keeps brute force attacks impractical, protecting our digital security. It's not just about counting, it's about understanding the structure of complexity itself. So, combinatorics is the hidden force that explains how possibilities grow, why some problems are easy while others are impossibly hard, and how algorithms manage to find needles in massive haystacks of data. In our next episode, we'll move into algorithmic complexity and computability, exploring the famous P versus NP problem, the limits of computation, and how efficiency defines the power of AI models. Don't forget to follow us by clicking the link below and check out the full playlist in the description. This journey into data, algorithms, and computation is just getting started, and trust me, you won't want to miss what's coming next.